So, last time did some division and some fractions, and we'll do some more of that as well. But I wanted to start off today introducing the notion of, well, first I wanted to go over the distributive rule again, very important, and then talk about powers, which is kind of the last arithmetic operation, of the basic number stuff. All right. So, first, the distributive rule. So, I've mentioned this before, but a basic fact of multiplication is if you have an expression like this, like 3 times this quantity 2 plus 4, so think of a multiplication symbol there, but usually there isn't one. It's just a number in front of some parentheses. Or even a letter. The claim, distributive rule, is that this is the same as if you were to distribute the 3 inside the parentheses, like that. So you can distribute a factor outside of a parentheses in. It also means, going this way, you can factor out the 3. So both directions are important to have in mind. It's really the fundamental thing in algebra that trips students up all the time. It's used all over the place, and so there you go. Just to demonstrate in this one example, 2 plus 4 is 6, 3 times 6 is 18, and over on this side we have 3 times 2 is 6, 3 times 4 is 12, 6 plus 12, 18. So there's 2 different ways of doing it. In a more picturesque way, if you think of rows and columns, 2, 3, 4, 5, 6. Here we have 4 columns, and over here is 2. And so, if I just look at this part of the problem, this is like 3 times 4. If I look at this part of the problem over here, it's 3 times 2. And the whole thing, is also 3 times 6, number of columns times the number of rows. So that's sort of why the distributive property works in some ways. And to also start down the road of algebra, I'm going to start using some letters. So over on this side, all right. Can you see that part of the board? Yeah, okay. The distributive rule in general is A times B plus C is equal to A times B plus A times C. And also A times B plus A times C factors into A times B plus C. So here the letters A, B, and C represent any numbers whatsoever. This is how we write it in terms of it kind of something always being true. You put in any numbers, and that's what's true. That's the distributive rule, multiplying the number inside the parentheses, and it's factoring when you go the other way. All right. Now, I said this works for any numbers, and that includes fractions. So I mentioned some stuff about fractions before, and I'll do some more stuff later. But in terms of the distributive rule, and factoring, so if I wanted to add up 3 halves plus 5 halves, for example. The distributive rule is one way of understanding kind of just adding the numerators here. Because this is the same thing as thinking of 1/2 as a number, and we have 3 plus 5. So that distributive rule is underlying a lot of fraction addition. We're multiplying this 3 plus 5 by 1/2 on this side, and over here, you know, we have 3 halves plus 5 halves, and we think of 3 halves as basically 3 times 1/2, and 5 times 1/2. 1/2 is just kind of a new number. It's a new thing. And this is sort of what we mean in some sense by this. And so our distributive rule kind of almost guides us to what it needs to be, which is 1/2 times 8, or 8 halves. And that kind of reduces to 4. Talk more about reduction a little bit later. But just want to emphasize how important this rule is. Whenever you're trying to tackle algebra, you need to be totally comfortable with this rule. And a lot of things in math either come down to using this rule or not, or avoiding using the rule when it's not appropriate. Horrible things are done in the name of the distributive rule. Okay, so that's the distributive rule. Next up, powers. So addition was kind of like repeated counting. You keep adding something to something, you're counting it up, you're counting up the number of ones. Addition is just sort of this shortcut to not have to actually count out all those ones. Multiplication was repeated addition. Like 3 times 5 is 3 plus 3 plus 3, 5 times. You add that up, so that's a shortcut. Well, powers is a way of doing that for multiplication. Powers, also known as exponentiation, is repeated multiplication. So, for example, 5 cubed, or 5 raised to the power 3. We write it as 5, and then we have a superscript 3 here. So it's on its own kind of level. On a keyboard, it would be the caret symbol when inputting things. Anyway, and what it means is 5 times 5 times 5, which is 125. But the main point is you're multiplying 5 by itself 3 times. All right. Now, is 5 raised to the power 3 the same as 3 raised to the power 5? No. So 3 to the 5, which is 3 times 3 times 3 times 3 times 3, is, anyone know? I've got a number in my head. So That would be 9. This would be 27. 3 times 9 is 27. The next one up is 81. And then there's 243. So is 243 the same as 125? Nope. So they're not the same. 5 to the 3 does not equal 3 to the 5. Not equal. So that's what powers are. They're used quite a bit in various contexts. As I hope you can see from this example, numbers start to get large very quickly. 5 to the 3 is already 125. 5 to the 4th would be, I think, 625. And then 5 to the 5 would be another, on the order of 3,000, and so forth. It grows very quickly. So that's that. Now, there are some rules of dealing with powers. Basically, let's say I take 5 to the 3 and I multiply it by 5 to the 2, which is 5 squared. So for raising something to the power 2, it's squaring. For raising things to the power 3, it's cubing, and everything else you just say the power. Anyway, how can I simplify this? Not really simple. Write it in another form, I suppose. Well, how many 5s in total am I multiplying together here? Amber? Yeah. So if you write it all out, right, so this is 5 to the 3, and over here is 5 squared. Can't even say 5 to the 2. That's literally what I'm doing here, and there's 5 5s, and so it's 5 to the 5. And how could I do that without doing this? Well, 5 to the 3 plus 2 is 5 to the 5. So one rule is rules of powers. So if you have two numbers you're multiplying together, like this with the same base, you can add the exponents. So I should probably write that somewhere. This number a is called the base. So it's the number you're multiplying by itself over and over again. And this number is the exponent. And so when you're multiplying two things with the same base and you have the exponents, you just add them. And it's just because you're counting that number of factors. So it's a nice, easy rule to enjoy. Now, another thing one can do is, so I've got something raised, say, to the second power, 5 squared, and now I raise that to the third power. How does that factor into things? How many 5s do I have in total? Well, kind of by definition, I have 3 5 squareds here, And then each 5 squared is itself 2 5s. And so that's 5 to the 6th. And how is 6 related to 2 and 3? Remember? Yep. 5, 2 times 3. So, and basically it's because when you're raising this thing to the 3rd power, you're having 3 copies of this, and so you're adding 2 to itself 3 times, and that's multiplication. So that's 2 times 3. So a to the b raised to the c is a to the b times c. And you can see the definitions of addition and multiplication coming through in all of these things as well. It's nice how things fit together. Let's see, what else do we have with powers? So, let's say I've got 3 squared times 2 squared. Can I do anything with that other than multiply it all out and give you a number?
You said you only merge the exponents if the like base number is the same, right?
Right.
So no.
So I can't add. So like I can't do something like 3 to the 4th, right? That wouldn't even make any sense. You might try to want to do something like that. So mostly all you could do is multiply it out and get 36. However, because I've got like the same powers here, if I wanted to, I could write this as kind of pull out the squares, so it's kind of like a distributive rule. And why does that work? Well, so 3 squared times 2 squared is 3 times 3 times 2 times 2. All right, and what's this thing? This thing is 3 times 2 times 3 times 2. And these two things are equal because you can just flip the multiplications. So basically a times b, to the c is a to the c times b to the c. So you have for a power outside of a product, you can distribute it inside or factor it out, depending on what you're trying to do. Now, what about 3 plus 2 squared? Can I do anything with that? So the really horrible thing that's knifed through my heart, I see people doing it, is they want to do this. Right? Just bad. You can't distribute powers across a sum. And why? Well, I'll try it. So 3 plus 2 squared is 5 squared is 25. 3 squared plus 2 squared. 3 squared is 3 times 3, which is 9. 2 squared is 2 times 2, which is 4, and that's 13. And these two things are simply not equal. You simply can't do it. It's not true. So it's kind of like addition's relation to multiplication is a lot like multiplication's relation to powers. So it's like you're kind of going up this hierarchy of these operations. Alrighty. So there's that. What else we got? So say 3 squared divided by 3. So 3 squared is what? 9, right? And you can divide 9 into, 3 divided into 9 is 3. All right, so that's kind of hopefully what we know. Over on this side, this is where the power stuff gets a little both weird and cool, is you can bring numbers in the denominator or bottom of a fraction up as a negative power, then you add them. So this is, you can view this 3 on the bottom as 3 to the minus 1. So a negative power is about fractions, and then we can add them, and then you get 3 to the 1, which is just 3. So this is where some real fun begins, with being able to view numbers as powers of numbers, and then you can kind of do just addition and subtraction and get rid of stuff. So so 1 over a to the b is the same as a to the minus b. All right, that's kind of a quick overview of powers. In addition, how do we undo addition? What's that operation? Subtraction? That's how we undo addition. Multiplication, how do we undo multiplication?
Division?
Yep, division. With powers, we undo them with something called, well, it's kind of also a power, but undo powers with kind of fractional powers. Somewhat called roots. I don't really know why it's called a root. But so, for example, so if I had like 2 squared, I would raise it to the power of 1/2. And over here, the outside power comes in and multiplies. And so formally, that just is sort of how it's undone. And a special symbol for for this is the square root of a number. Square root. Yeah. So 2 squared is also 4, so you might see square root of 4 equals 2. And what this means is 2 is the number whose square is 4. So it's kind of defining it in just as undoing, raising something to a power. Now, in general, taking the square root of numbers is not going to be nice. I'll talk about that more some other time. But for example, the square root of 2, for example, is something like 1.41, blah, 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 blah. And it just goes on forever, no repeating patterns, no nothing. It's a whole another new kind of number called an irrational number because you can't write it as a ratio. Yeah. And, it's not entirely irrelevant to reality because as it happens, if you had a square with lengths 1 on each side, this line between the two vertices would have length square root 2. So it actually does exist. It comes out, mostly exists. Maybe you can't actually make a square with side lengths 1 in reality. Who knows? But at least conceptually, that's what it is, and it's a whole story behind that too. But anyway, just kind of a taste of powers, basically exponents. It's the same kind of stuff that was with addition and multiplication, but on kind of another level. It plays nicely with multiplication. It plays horribly with addition. All right. Okay. Enough of powers. Yeah?
When you write stuff on that side of the board, you can't really see it until you step away because there's no room there. So do you consider that for the viewers?
Okay. I was just trying to put some rules on there. I don't
Sure.
generally.
Yeah. It helps to see stuff as you write it, as you say.
Yeah. It also helps to have a clean board, but oh well. Okay. If you recall last time, I had mentioned this technique called of kind of checking out whether you've done the operation successfully or not by kind of adding up the digits. And so like here, 8 plus 7 is 15, plus 3 is 18, plus 2 is 20. Add them up again, 2. And my claim was that this is the remainder when we divide by 9. So let's do it. So 9 divided into 8732. So 9 into 87, the closest number under 87 that 9 divides into or whatever nicely is 81, and that's 9 times 9. And so this is kind of I'll do the standard technique for a moment. 9 times 9 is 81. I do a subtraction. I get 6. I bring down the rest. 9 into 63 is 7. 7 times 9 is 63. Subtract that. You get 0, 2. 9 into 2 ain't going to happen. And so 970 with remainder 2. is my answer of dividing 9 into 8,732. You just do it 2 digits at a time, subtracting out until you're left with something that's less than 9, and then you're kind of done. And remember that what this meant was 970 times 9 plus 2 is equal to 8,732. And if you want to check it out, do that multiplication, add the 2, and you should get 8,732. Now, the main point I was trying to get out here is that doing this division by 9, you get a remainder 2, and that's what I got when I summed up all these digits, which seems kind of weird, right? Hope that feels weird. Does that feel weird? A little bit weird? No more.
Specifically when you divide by 9?
Yes. So if I can try, well, so for example, if you divide by 2, right? This is actually an even number, so you can divide by 2. And so there's no remainder when you divide by 2. And in fact, you can never get a remainder of 2 with dividing by 2. So this is very specific to dividing by 9. And sort of the question is, what is special about 9? Is there a number that 9 is close to? It's buddies with 10. Yep. And what special role does 10 play in our number system? Amber? And more specifically, it's this, like, the powers of 10 is how we write out our numbers, right? So 8,000, that's 8 times 1,000, 7 times 100, 3 times 10, and 2. So 8,000 is 8 times 1,000 plus 7 times 100 plus 3 times 10 plus 2. That's literally what we mean when we say 8,732. Basically, I'm even saying it when I say it. But now, how does 9 appear? Well, as we said, 10 is very close to 9, right? It's 9 plus 1. What about 100? Is there something relating to 9 that's very close to 100? Maybe something with 2 9s? 99. So 7 times 99 plus 1, and 8 times 999 plus 1. All right. So take a moment and see that I've done absolutely nothing yet. Right? This expression is the same as this. 999 plus 1 is the same as 1,000. 99 plus 1 is 100. 9 plus 1 is 10. I've just rewritten the thing. Totally harmless. Pay no attention. And now, what's the rule? The rule I'm going to use starts with a D. Distributive rule. Told you it was important. 8 times 999 plus 8 plus 7 times 99 plus 7 plus 3 times 9 plus 3 and plus 2. And just write distributive here. So we've got the distributive rule doing this. Now I rearrange some terms. 8 times 999 plus 7 times 99 plus 3 times 9. And then 8 plus 7 plus 3 plus 2. All right, so this, what is this? This is the sum of the digits. And of course, that's because I had this plus 1, which when I distribute, gives me the sum of digits. And this thing is 9 times 8 times 111 plus 7 times 11 plus 3. Right? What did I do here? Factored out the 9. Reverse distributive rule. 9 times, if you want to check, you can distribute it back. 9 into this thing, well, 9 times 111 is 999. 9 times 11 is 99. And 9 times 3 is 9 times 3. So I've got 9 times something, don't really care what it is, plus this thing. So 9 whatever plus 20. And so when I divide by 9, so I put that all over 9, those 9s cancel. Again, distributive rule. And then I'm left with 20 over 9. So that's a new division problem. I sum up those digits again, I get 2 as the remainder. That's where the 2 comes from. But you can also, 20 is 9 times 2 plus 2. Anyway, so the 9 would divide into this fraction, and this is going to be the remainder. So basically, well, this is your first exposure to the kind of crazy manipulations that happen in algebra, but only it's just with numbers. So there's that. Distributive rule, rewriting things in an inspired fashion. That's the hard part, being inspired. And just playing it out to a conclusion. So, and if you compute this out, you'll get almost the thing I got from division, but 2 less because of that. Anyway. Okay. Check something. What time is it? 2:06. All right. Okay. Let's see. I think I haven't done 2-digit division yet. So let's take a look at a problem like that. I don't know. 28 into 384. So basically, what do you do? So if you just had 28 into 38, what do you get? So 28 would go into 38 only one time, right? And this is how we'd kind of write it. As 10, so it'd be kind of like you'd have a remainder of 10, and basically it's just 38 is equal to 28 times 1 plus 10. So that's that problem. And now when you translate up to here, it's essentially the same thing, except when we write that 1, this is kind of like a 10, right? That's what that positioning means. It's over the tens. And so 10 times 28 is like 280. And so you subtract that, and you have 104 kind of remaining. This 10 here was the same as this 10, but because we have another digit over here, we have the 4 coming down. And then how many times does 28 go into 104? Well, so this is where it gets a little bit harder than with a single digit, because it's a little harder to know these things, right? But roughly speaking, 28 is almost what number? 25 or 30? I'd probably go with 30. So kind of in your head, 28 is kind of close to 30. And so, and this is kind of like 100, more or less. So what's something that's a multiple of 30 that's under 104? You got 30, 60, 90, 120, right? 120 was too much, so the 90. So it's kind of like 30 times 3 is like 90, and 30 times 4 is 120, so I'm going to try 3. So I try a 3 here, and one thing to kind of help orient yourself is to have it in mind that it's kind of like around 90, and so you would kind of expect something like 90 being down here. So 28 times 3 over here is, you can do a 60, and then 3 times 8 is like 24, and so you've got 84. So we write down 84 here. And so 104 minus 84 is 20, and so that's the remainder. So the claim would be 28 times 13 plus 20 is equal to 384. If I've done all that correctly, that's how it should go. Now, one could actually do that multiplication out, or you can do the checksum thing, add up the digits, multiply those things, and compute all that out. In any event, 2 digits dividing into other things, it gets harder, but it's mostly the same kind of reasoning and thinking. As far as I can tell, looking around, talking to my wife who used to teach this kind of stuff, this stuff is kind of only like put up there a few times or something and then kind of moved on because it's kind of painful. Particularly like the techniques that they tend to use involve a lot of guess and try and manipulations, and I don't know. The book that I like does have some stuff, but not sure it's really worth getting into because, honestly. What's probably more important is just having in your mind like rounding and getting a sense of these things. So like 28 into 384, you know, inside my mind I might think of this as sort of like 30, and like this. I might try to think of if I have a nice multiple of 30 in my mind, so maybe like that's 360, which I sort of know as 3 times, 100, or well, I guess 30 times 12. And so the answer is kind of 12. Like, that's probably the first thing you might want to do with these problems to get a sense of the number. So clearly it's not right. It was 13, and it wouldn't tell you the remainder, but it tells you basically roughly what to expect. And so if you do embark on one of these computations, or you take out a calculator and you compute it all out, if it's nowhere near 12, that's an indication you've probably made a mistake somewhere. All right. All right, let's go back to fractions. So I said last time, fractions are the most fundamental thing that kind of comes out of remainders and divisions. And then decimals were a special kind of fraction. These are powers of 10. And percents are a special kind of decimal where it's, you've kind of shifted the decimal point 2 places. So at the heart of everything are fractions. And so what does something like 1/2 mean? Means what? So one definition of it would be just, so it's kind of a new quantity. So in some sense, it's just this new thing. Like, we started with the counting numbers, 1, 2, 3, they were mapping these things. And then eventually we came across like -2, right? Which doesn't really fit with the counting, but it's kind of a new number. And we make sense out of it. We say this is how it fits in with the operations and makes sense. And maybe you can spin a story like if you have -$2, that means you owe $2 to somebody, right? You can make that, but it's sort of just a new thing. And the same thing is with fractions. It's a new quantity, and it's trying to represent division, just in the same way negative numbers represent subtraction. Fractions kind of carry along that division. And one way of thinking of this is I don't want to think that way. Represents divisions. So, sort of like 1/2 represents something which 2 of it represents, oh, 2 of it becomes 1. So if you had a box and you call that 1, maybe it's kind of a stick or something, that's your basic unit. 1/2 means you divide that 1 into 2 pieces, 2 equal pieces. And basically this is what 1/2 represents, that sort of area. And 1/3 would represent cutting up this box into thirds. And you'd have one of those boxes filled, and that's what represents 1/3. And then you have the whole thing, divide it up into 3 pieces, and you get that. Now 2/3, well, that would represent cutting the box up into 3 pieces and then taking 2 of them. So that's 2/3. And if I wanted to do, say, 1 plus 2/3, well, so I've got, this is my 1/3, this is my 2/3. I add them together, and what do I get? I get 3 1/3. Guess I should put parentheses here. There's a notation that you don't want to make a mess of, but sort of like 3 1/3, and that's just your entire thing, which is 1. So another way of saying it is, for example, 1/3 solves the problem of finding a number, so let's call it x, such that 3 times x equals 1. So it's like we're creating this new thing that has some uses, and it actually allows us to solve questions that we wouldn't be able to solve. You cannot find a number out of like kind of whole numbers, counting numbers, such that 3 times that is equal to 1, right? You just can't do that. But I create this thing called a third, then 3 times 1/3 is 1. And it's basically just what that means. And again, what does 3 times a third mean? You know, in terms of addition, it's just multiplication by this number is adding it to itself 3 times. It's taking 3 of these segments, adding them together, and you get 1. Okay, so hope I've conveyed the sense that a fraction is this new thing. It represents breaking things up into wholes, into pieces, I mean, and something like 2/3 can be thought of as like 2 times 1/3. It's sort of, that's kind of what it means. Okay. All right, so we know how to add things when you've cut the thing up into the same base parts. what about adding stuff with different denominators? So 1/2 plus 2/3. So pictorially, we're trying to take that 1/2 and divide this up into thirds, and you've got 2 of these 3 parts, and you want to somehow add them. And so what do you have to do? One way of thinking of these fractions is kind of like units. So like you've got no time left. Minutes and seconds, right? If you have 3 minutes and 57 seconds, and you want to combine that into a single number, what do you have to do? You can't just like take the 57 plus the 3 and get 60 seconds, right? That doesn't make any sense. You have 3 minutes and 57 seconds. You have to maybe change the minutes into seconds. 3 minutes, 60 seconds, each minute, 180. And then you can add them, right? You get this commonality, you get this common description. It's the same thing with fractions. While this quantity is perfectly defined this way in terms of whatever, you can't get your hands on it, you can't simplify it without changing the units. And so if I see this 3 here, so I know this is divided into 3 parts, so I want to divide my 1/2 kind of into 3 parts. So I'm going to just divide up there. And then this 3 I'm going to divide into halves. And then I count. So I write 4, 6, 1, 2, 3, 4. There's 6 parts I've divided this thing into. There's 4 of them there. And over here, I've got 3 parts. And again, there's 6 total that I've cut this thing up into. And so what I can say is 1/2 is 3/6, and 2/3 is 4/6, and so I have 7/6, and that's 1 1/6. And kind of think of a plus sneaking in between here. It's bad notation because it makes me want to multiply, but it's called mixed fractions. It's terrible. Anyway, we change the bottoms to be the same, and then we can add the tops. So we change it into 6, we add that. And if you look at it, what I did here basically is I multiplied the top and the bottom of 1/2 by 3, and I multiplied the top and bottom of 2/3 by 2, which gave me the 3/6 plus the 4/6. So if you think of fractions in terms of units, when you add fractions of kind of different bottoms, you need to change those units. And I guess with that, we're done. I will have to do more fractions next time.